Hello everyone. So in this video, I will be covering all concepts, all derivations and all possible numericals that can be asked in your board exams from the chapter Moving Charges and Magnetism. So first we'll go through the syllabus and then we'll cover each and every concept in this video. So first we'll go through the magnetic field and then the Oersted experiment, and with this experiment we come across that if there is a current carrying conductor, it produces magnetic field. Then a Biot-Savart law, with the help of Biot-Savart law, we can find magnetic field via the current element. And we have to also study the application of Biot-Savart law to find magnetic field produced by a current carrying loop. Then Ampere's law, with the help of Ampere's law, again we can find magnetic field. Its application to find the magnetic field produced by a infinite current carrying conductor. Then the qualitative concept of solenoid, and then the force on a moving charged particle in electric field and magnetic field. Then we'll study force on a current carrying conductor placed in uniform magnetic field. Then if we have two current carrying conductors or two current carrying wires, then what is the force of attraction or repulsion between them? Then we'll also see the definition of 1 ampere and then the torque experienced by a current carrying loop placed in uniform magnetic field. Then we'll study current loop as a magnetic dipole and the formula of magnetic dipole and how a current carrying loop behaves like a magnetic dipole. Then the moving coil galvanometer, what is its current sensitivity and how we can convert galvanometer into voltmeter and ammeter. Right. So now let us see what is magnetic field. So it is the region or space around a magnet or a current carrying conductor or a moving charge in which its magnetic effect can be felt. For example, if there is a bar magnet and if I place a compass needle here, so this compass needle shows deflection, right? It shows some deflection. So if it is showing deflection, we can say there must be a magnetic field which has applied force on the needle and it has deflected. Okay, right. So what is the unit of magnetic field? It is measured in Tesla, and its CGS unit is Gauss, and 1 Tesla is equivalent to 10 raised per 4 Gauss. And you should also remember the dimensional formula of magnetic field. It is m raised per 1, L raised per 0, T raised per -2, A raised per -1. And how we can generate a magnetic field? So we can produce magnetic field with the help of a current carrying conductor. We can produce by a changing electric field. So changing electric field induce magnetic field. And if there is a moving charged particle which is moving with uniform velocity, it can produce magnetic field. And then with the help of a permanent or a electromagnet. Now if the magnetic field is into the plane, so I'll show it with a cross. And if it is out of the plane, I will show it with a dot. These are the normal convention that we use for magnetic field. Right, so what is Oersted experiment? So with the help of this experiment, Oersted was able to figure out that if there is a current carrying conductor, it can deflect a compass needle. So let us see the setup. So we have given a battery, and this battery is connected with a switch. There is a switch, and we have a wire, right? There is a wire like this. Now when we close this, and let us say before closing the switch, we have placed a compass needle just below the wire. And let us say this direction is north, so the needle is pointing in the north direction. Now when we set up current, when we close the switch, then there will be a current in the clockwise direction. So there will be a current in this wire is in the downward direction. Now due to this current, there will be a magnetic field produced by this wire, and this magnetic needle will start pointing in the right direction, right? So it is pointing in the right direction, so there is a deflection. So with this deflection, Oersted was able to figure out the direction of the magnetic field. So how we can find the direction of magnetic field by a current carrying wire? So we can put our thumb in the direction of the current, and if I curl our finger, then the direction of the curl will give you the direction of the magnetic field. So for example, in this case, thumb is pointing in the upward direction and we are curling finger in this direction, right? Got it? Similarly, if the current is going in the downward direction, then if I curl the fingers, thumb is in the downward direction, and in the direction of the curl, we have the magnetic field. So magnetic field will be in the concentric circles like this. So that we have to remember. Let me give you the idea of the direction. Let us say this is the x-axis, this is the y-axis, and this is the z-axis. And there is a current carrying wire which is along the, and it is having current along the positive z-axis. So this is the direction of current. So if I draw a circle with a center at the origin in the xy plane, so the magnetic field will be along this circle. So at this point on the x-axis, if I curl my finger, the field at this point on the x-axis will be in the positive y direction, and the field at this point on the y-axis will be in the negative x direction, and the field at this point on the negative x-axis will be in the negative y direction, and the field at this point on the negative y-axis will be in the positive x direction. So like this we can find the field by a current carrying wire. Okay, now next concept is the Biot-Savart's law. So with the help of Biot-Savart's law, we can find magnetic field by a current element. Now what is a current element? So this is a wire, right? Let us say this is a current carrying wire. Now we have taken a small element of this current carrying wire, and the length of this element is dl, and the direction of dl will be in the direction of the current. So this is dl vector and it is in the direction of the current. So current is going in this direction. So we can say current element will be I times dl, and its direction will be same as the direction of the current. Now if I want to find the field at point P in space, so what are we going to do? We'll draw a position vector from the current element to the point P, right? So R is the position vector of P with respect to the current element. And the angle between the dl vector and the position vector of P is theta. So with experiments, Biot-Savart was able to figure out that the magnetic field produced by this current element will be equals to mu naught upon 4 pi I dl cross r vector upon r cube. Now it's a mathematical relation, and this constant of proportionality, its value is 10 raised to power minus 7 in SI units. Now let us see. So mu naught will be, so we know that mu naught by 4 pi is 10 raised to power minus 7 Tesla meter per ampere, and mu naught will be 4 pi times 10 raised to power minus 7. So you have to remember mu naught value, and mu naught is known as the permeability of the medium. So it's the property of the medium. So mu naught is permeability of free space. So if we change the medium, mu value will change, and eventually the magnetic field will also change, right? And there is another term which is known as relative permeability, mu r, which is the permeability of the medium divided by the permeability of the vacuum or the free space. And you should also remember the dimension of mu naught, and we can very easily find dimension of mu naught if we know the dimension of magnetic field. And it comes out to be m raised to power 1, l raised to power 1, t raised to power minus 2, a raised to power minus 2. And the direction, so whenever we talk about magnetic field, which is a vector quantity, so along with magnitude, we should also know what is the direction. So can you see in the numerator, we have dl cross r. So it will be in the direction of dl cross r. How to find the direction? Let us say in a plane, this is a dl vector and this is the r vector. Now if we curl our fingers from DL to R with the help of right hand, so if I apply right hand curl rule, we can find the direction of the cross product. So if this angle is theta, so this is the direction. So it will be normal to the plane containing both the vectors. So this will be the direction of dB. I hope it is clear. Now let us see how we can use Biot-Savart law to find the magnetic field produced by a circular coil. Now we have given a circular coil and it is having a current, let us say I, in the clockwise direction. Now we are going to consider a very small element, or you can say the current element, dl. So this is the current element, and due to this current element, so now we want to find the magnetic field at the center. So I will draw the position vector of the center from this current element. So this is our r vector, and clearly we can say this r vector is nothing but its magnitude is nothing but the radius of this coil, right? And a dl vector is in the tangential direction, so the angle between r vector and the dl vector will be 90 degree. So if I apply Biot-Savart's law, then dB will be mu naught upon 4 pi I dl cross r vector upon r cube. Now here dl cross r will be what? So dl cross r is dl r sine theta, right? And sine theta in this theta will be 90 degree. So this will be dl times r, that is the magnitude. dl times r. Now what is the direction? So it will be in the direction of dl cross r. So dl is in the right direction. So if I curl my fingers from dl to r, the thumb is pointing into the plane. So the magnetic field at the center by this current element will be into the plane. And you can also find the direction of magnetic field by curling your fingers in the direction of the current. The thumb will give you the direction of magnetic field, right? So there are two ways. Either you can use dl cross r. If you're comfortable with that, you can find the direction. If you're not comfortable with that, you can use right hand curl rule. You can curl your fingers in the direction of the current. Thumb will give you the direction of the magnetic field at the center. Okay, now if I substitute these values, so we have mu naught upon 4 pi I dl r upon r cube. So this will be mu naught I upon 4 pi r square times dl. Now this r is small r is nothing but the radius of the loop. Let us take it as r. So this will be mu naught I upon 4 pi capital R square dl. Now this is the magnetic field produced by this small element. If you take any other element, the magnetic field produced by that element will be into the plane. So if it is into the plane, we have to simply add all these fields and we will get the magnetic field produced by the current carrying loop. So if I integrate this, so mu naught I upon 4 pi r square is constant, so it will come out of the integration. And we have integral dl, and integral dl is nothing but the total length of the loop, that is the circumference. So we can say magnetic field at the center will be mu naught I upon 4 pi r square times 2 pi r. So we'll get 2 in the denominator, one r will get cancelled out, so we'll get mu naught I upon 2r, right? So this is the formula for a single loop. Suppose if we have two loops, so in case of two loops, we'll multiply magnetic field with 2, right? If we have half loop, we can multiply this with half, right? So this formula, so I can just write down, the general formula. So it will be mu naught I 2r times n, and this n is the number of loops, and this n can be fraction. If you have a one complete loop and other half loop, then this n will be 1.5. So this n can be fraction, right? Can be fraction. Still the magnetic field will be into the plane at the center. So I hope this concept is clear to you. Now let us see what is the magnetic field at a point on the axis of the loop. So let me derive that. So we have given a current carrying loop and let us say the current is in this direction, and let us take the radius of the loop as r, and we want to find magnetic field at a point P on the axis, which is at a distance x from the center of the loop, right? So what I'm going to do, I will take two elements, diametrically opposite elements. So first I will take a current element at the top. So we can say here the current is entering into the plane, right? It is entering into the plane, and this is our current element IDL. Now due to this current element, the position vector of point R will be this, right? So if you look at this, the plane which contains current element and this R vector, the normal to that will be in this direction. So if I apply dl cross R, the thumb is pointing in the normal to this plane. So this is the direction of magnetic field, which is dB, let us say. Got it? So this is the direction of magnetic field. Now if I consider a current element at the bottom on the diametrically opposite end, so let us say it is pointing in the out of the plane. So due to this current element, dl cross R, it will be normal to this, right? So this is dB, right? So by symmetry, we can say the component of dB which is normal to the axis will get cancelled out, and the component which is along the axis will add up. So let me take some angles. So if this angle is theta, right? If this angle is theta, then I can say if I draw a vertical, then this angle is also theta, right? Similarly, if this angle is theta, we can say this angle is also theta. Now we can take the component of dB. So there are two components. One will be in the vertically downward direction, so dB cos theta, and it is having component dB in the upward direction, cos theta. And these two components will get cancelled out because of symmetry, and we are left with only horizontal component. So this will be dB sin theta and dB sin theta, right? So we know what is dB. dB will be mu naught I upon 4 pi, then dl cross R by R cube. Now in this case, dl and R vector are perpendicular to each other. So this will become mu naught I dl times R upon 4 pi R cube. So this can be written as mu naught I dl by 4 pi R square. Now what is R square in this case? R square is this, right? This hypotenuse. And this is root of R square plus X square. So X is constant because we want to find the field at a particular point. R is constant. So I can say this small r is also constant. So we have only dl. So dl is the only thing on in this equation which is variable, right? So dB. So this is dB. So if I want to find the magnetic field at point P, so we have to find the sin theta component. So this will be mu naught I upon 4 pi R square and sin theta. So dl and sin theta can be written as perpendicular upon hypotenuse. So perpendicular is R and hypotenuse is nothing but small r. And now we have to integrate this. So mu naught I R upon 4 pi small r cube will come out because it is constant, and then we have integral dl. Now what is integral dl? It is nothing but the total length of the loop, which is the circumference, that is 2 pi r. So mu naught I R 2 pi r divided by 4 pi r cube, and r is root of r square plus x square, so that will be r square plus x square raised to power 3 by 2. So this 5 will get cancelled out, we'll get 2 in the denominator. So we got our formula, and this is b mu naught I r square divided by 2 times r square plus x square raised to power 3 by 2. Now this formula is due to a single coil. If we have say n coils, if there are n turns in this coil, then for n turns, and here n is an integer, right? A whole number. For n turns, B will be mu naught I r square by 2 r square plus x square raised to power 3 by 2 times n. Do remember this n is natural number 1, 2, 3, 4, 5, something like that. It can't be a fraction, right? If it is a fraction, in that case the field is not along the axis. It will be in some other direction. So do remember this, and usually you will get the application of this formula only. And this derivation is also important. So do practice this derivation. Okay, now there are two special cases. If I write down the formula, it is mu naught I r square n upon 2 x square plus r square raised to power 3 by 2. Now, if x is very large in comparison to r, then what this formula will reduce to mu naught I r square n upon 2. So we can ignore r in terms of x, right, in the denominator. So this will become x raised to power 3. Got it? So magnetic field becomes this. And this magnetic, so here basically the current carrying loop is behaving like a magnet or magnetic dipole, right? So we'll I will again come back to this particular section when we'll discuss magnetic dipole in this video. So do remember this formula. Now, if x is very small in comparison to r, then we can ignore x in terms of r, and the magnetic field will become mu naught I r square n divided by 2 r cube, which becomes mu naught I n by 2r. And that is the same formula that we have derived for circular coil. Okay. Right. Now let us see a question which came from the same form, which you can answer by using the same formula. So two very small identical circular loops 1 and 2 carrying equal currents I are placed vertically with respect to the plane of the paper with the geometrical axis perpendicular. So their geometrical axes are perpendicular, and it is already given in the diagram to each other as shown in the figure. Find the magnetic magnitude and the direction of the net magnetic field produced at the point O. Okay, right. So one thing I forgot to mention, how to find the direction of magnetic field at point P on the axis. So what you can use, you can use the right hand curl rule. You can curl your fingers in the direction of the current. The thumb will give you the direction of the field. So here the magnetic field, so if I curl my fingers like this, the thumb is pointing in the left direction. So the magnetic field at P is towards the center of the coil. So in this case, for this coil, if I curl my fingers like this, the magnetic field is pointing in the left direction at O. So this is B1. And for the second coil, if I curl my fingers in the direction of the current, thumb is pointing in the upward direction. So this is B2. And by symmetry, so we have two identical coil, B1, B2, their magnitude will be same. If their magnitudes are same and we have two vectors which are perpendicular to each other, then the resultant, so B at O will be root 2 times B1. We can write it like this. Now what is B1? B1 is mu naught I, and the radius, let us take it as R square upon 2 times x square plus r square raised to power 3 by 2. Now if I multiply this with root 2, this is the magnetic field at point O due to these two current carrying coils. I hope this concept is clear to you. Right, now let us see one more question. So two identical coils, each of radius r and number of turns n, are lying in perpendicular planes such that their center coincides. So something like this. Let me show you. This is one coil and this is another coil, and their centers are coinciding, and the radius is r and the number of turns in both the coil is n. Find the magnitude and the direction of the resultant magnetic field at the center of the coil if they are carrying current I and root 3 I. So they have different currents, but their dimensions are same. So let us say in this coil, the current is I. So if I apply right hand curl rule, so thumb is pointing in the upward direction, so it will be in this direction. So this is B1, let us say. And in the second coil, let us say the current is like this, and this current is root 3I. So if I curl my fingers like this, the magnetic field will be in the right direction. So let us find the magnitude. So B2 will be mu naught root 3I times number of turns divided by 2R and B1 will be mu naught I times N divided by 2R. Okay. So if I want to find the magnitude at the center or field, so it will be B net will be square root of B1 square plus B2 square because they are perpendicular to each other. Now mu naught I by 2R times N will come out, and we have root 3 square plus 1 square. So root 3 square is 3, 3 plus 1 is 4, and square root of 4 will be 2. So this will get cancelled out. So this is the net magnetic field at the center. And how to find the direction? So let us say the net magnetic field is making theta angle with B2. So tan theta will be B1 by B2. Now B1, so here we get 1, and B2 here will get root 3. So theta comes out to be 30 degree, right? Okay, right. So the next concept is Ampere's circuital law, and we use this law to find magnetic field by symmetrical current distribution. So let us say, we have given a loop, a circular loop, an imaginary circular loop. Right? And there are multiple currents which is piercing this circular loop. So let us say there is a current I1 which is piercing this loop, right? And there is another current, say I2 piercing, and there are some currents which are not piercing but they are quite close to this loop, right? Let us say this is I3 and there is another current I4, and let me take one more current I5 which is also piercing this loop. Now according to Ampere's circuital law, if I take a small displacement along the loop, let us say dl, right? I have taken a small dl vector along this loop. So I have taken it like this. So I have taken in a particular direction, right? If I look at it from the top, it will be in the anti-clockwise direction. So the currents which gives us the same direction, if I curl my finger, for example, I1 is in the upward direction. So if I curl my fingers, I'm getting anti-clockwise direction. If I take I2, again I'm getting the same direction. And if I take I5, the direction is reversed. Okay. So according to Ampere's circuital law, if you take the line integral over this loop B dot dl, it should be equals to mu naught times the current, the net current which is piercing the loop. And we should take I1, I2 as positive and I5 is negative, because for I5 the direction comes out to be different because we are integrating in this particular direction. But with the I5, if I keep my thumb in the direction of I5, the fingers are curling in the other way direction. So we should take it as negative. So in this case, the right hand side can be written as mu naught I1 plus I2 minus I5, and we should only take the currents which are piercing the loop, not the current which are not piercing. But if we talk about the magnetic field on the left hand side, this magnetic field will be due to all current elements, all sources. So at this particular point, there will be magnetic field produced by all the currents around. So I1, I2, I3, I4, I5. But on the right hand side, we have to take only the currents which are piercing. and the direction is also important. So we should first consider the direction of integration, and then we can decide whether we have to put a positive sign or a negative sign. Okay, let me give you one more illustration. Let us say this is the loop and there is a current which is piercing. This is the direction of the current, and let us say this is I1 and this is I2 and this is I3. Now if I take this direction as the direction of integration and this is a DL vector, so if I keep my thumb out of the plane for I2, right, for I2, the fingers are curling in the direction of the integration, right, in the anti-clockwise. So I will take I2 as positive. Similarly, I3 is also positive, because if you keep your thumb in the direction of I3, the fingers are curling in the direction of integration, in the direction of DL, right? But for I1, the thumb is pointing into the plane. So if I curl like this, it is opposite to the direction of integration. So in this case, I net will be I2 plus I3 minus I1. Got it? So that you should remember. And this displacement current I will cover in a separate video when we will cover electromagnetic radiation. So I hope it is clear to you. Now let us see how we can apply Ampere's circuital law to find magnetic field by infinite current carrying wire. So we have this kind of a case. So we have a infinite current carrying wire, and let us say the current in this is I. Now I'm going to consider an Amperian loop. Okay, and one thing I forgot to mention, this loop that we have taken, this loop is known as Amperian loop. So do remember this, Amperian loop. Like we have in Gauss's law, we take a Gaussian surface. In Ampere's circuital law, we'll take a Amperian loop. So when we have a line current, so when we have an infinite current carrying wire, in this case, I will consider a circular Amperian loop. Circular Amperian loop, and the center of this circle will coincide, or you can say it will lie on the current carrying wire. And if I look at it from the top, it will look like a circle, and the current is coming towards the source, towards the observer. Now this is the case, and if I consider this is our DL, right? And in Oersted experiment, we have seen if there is a current carrying wire, then the magnetic field will be concentric circles. So in this case, the magnetic field will be concentric circle and it will be in the anti-clockwise direction. So by symmetry, we can say at this particular point, the magnetic field will be in the direction of DL vector. So this is the magnetic field, right? So B and DL, at every point on this Amperian loop, the magnetic field will be tangential, right? So we can say B dot DL will be, it can be written as B DL cos 0, and cos 0 is 1. So B DL. And if I apply Amperian circuital law, B dot DL, so this can be written as closed integral B DL, right? And since by symmetry we can say B must be having a constant magnitude at every point on the Amperian loop, so we can take B out of the integration. So this will become B integral DL, and integral DL is nothing but the overall length of the loop. So this will be B times 2 pi R. Let us say this distance is R. So 2 pi R. So I have taken this as R. Now the right hand side of the Ampere's law is mu naught times the current which is piercing. So can you see this this wire it is having current I, and this I current is piercing the loop. So this will become mu naught times I. So the magnetic field by a infinite current carrying wire at a distance R will be mu naught I upon 2 pi R. So this formula we have to remember, because we're going to use this formula in some of the numericals. Right. So the next topic is solenoid. And what is a solenoid? Let us see. So if there is a cylindrical cavity or you can say cylindrical core. And on this cylindrical core, if we wrap a conducting wire, right? And in this conducting wire, if we set up some current, now this arrangement is known as a solenoid, and we can produce magnetic field by using it. So this is a case of real solenoid, right? So in real solenoid, there will be magnetic field all around, and the magnetic field will be quite parallel, or you can say the magnetic field will be nearly along the axis. So in this particular case, the current is flowing like this. And how we can find the magnetic field at the center of the solenoid? By using the right hand curl rule. So if you curl your fingers in the direction of the current, the thumb will give you the direction of the field at the axis, right? So this is a real case. But in case of an ideal solenoid, there will be no magnetic field outside the core. So at this region, the magnetic field is zero. At this region, the magnetic field will be zero. There will be only field inside the core. So this is known as the core, right? So this region is known as the core. And the magnetic field at the center of the solenoid will be given by mu naught Ni. So it will be a uniform field in case of an ideal solenoid. And how we can figure out that a solenoid is ideal or not? If the number of turns per unit length, so N is number of turns per unit length. If it is very large, and if you can say the length of the solenoid, if L is very large in comparison to the radius of the core, if this is R, then we can say we have a ideal solenoid. We can treat it as a ideal solenoid. Do remember this formula. It is mu naught Ni, where N is number of turns per unit length. So if number of overall turns in the solenoid is N, and if I divide this with the length, this length L, right? Then this gives you the number of turns per unit length. So the unit of small n will be meter inverse. And suppose if there is a question, what is the magnetic field at the ends of the solenoid? It will be half of the magnetic field at the center. So do remember these two formulas. The derivation is not required for board exams because it is clearly mentioned. We have to do the qualitative analysis. Right. So now let us see the application of the formula that we have studied as so far. Figure shows a long straight wire of circular cross section of radius A carrying a steady current I. The current I is uniformly distributed across the cross section. Derive the expression for magnetic field in the region R which is less than A and R greater than A. So let us see. So here we have a cylinder. You can say there is a cylinder which is having current. So in this case, I'm showing this in this view, right? I'm looking at the axis. So I will see a circle. So that is the cross section of the wire. That is the cross section, and the current from this cross section is coming out of the plane, let us say. So current is coming like this, right? So this like this the current is coming. So I'll show this with dots. It means out of the plane. So current is coming out of the plane. Now I want to find the magnetic field at a distance r which is less than a. Let us first calculate this. So I'm going to consider a circular Amperian loop, and its center will lie on the axis of the wire, and this radius is smaller, and the radius of the wire is given as A. So this radius is A. So let me show here. So this is A. And we have given that the wire has a this current I is uniformly distributed across the cross section of the wire. So I can define current density as I divided by pi A square. So how much current which is piercing this loop, that can be found out, right? And by symmetry we can say the magnetic field on this Amperian loop will be in the anti-clockwise direction, because the current is coming out of the plane. So I can show it like this. So this is the direction of magnetic field at different point on the Amperian loop. So again, I can say if I consider dl vector in the same direction, if dl is also in the same direction, then b dot dl can be written as b dl cos 0. So which is b dl. Now if I apply Ampere's circuital law, so integral b dot dl can be written as integral b dl, and b by symmetry has a constant magnitude on every or at any point on the loop. So I can take b out of the integration, and this integral dl is nothing but the circumference of this circle. So it will be 2 pi r. And the right hand side of the Ampere's circuital law is mu naught times the current which is piercing. So mu naught times the current which is piercing will be the current density multiply with the area of this Amperian loop, which is pi small r square. So from here, magnetic field will be mu naught j pi r square divided by 2 pi r. Now one r will get cancelled out, pi will get cancelled out. So we are getting mu naught j r by 2, and j is I upon pi a square, so mu naught r by 2 times I upon pi a square. So this will be mu naught I r upon 2 pi a square. So that is the magnetic field at a distance r from the axis inside the wire. Now let us consider the second case when r is greater than a. When r is greater than a, so I'm considering this as my Amperian loop, and for this loop r is greater than a. And by symmetry, I can say the magnetic field will be in anti-clockwise direction at different points on this Amperian loop. And by doing the same working, integral b dot dl can be written as b integral dl, which will be b times 2 pi r. And the right hand side will be mu naught times the current which is piercing the loop, and in this case the entire wire is piercing, so we can say the current piercing will be I. So b will be mu naught I upon 2 pi r, right? So that is the answer of second part, right? So now let us see this illustration. So two long coaxial insulated solenoid S1 and S2 of equal length are wound over one over the other as shown in the figure. A steady current I flows through the inner solenoid S1 to the outer end B, which is connected to the outer solenoid S2, through which the same current I flows in the opposite direction. So for example, if in the inner solenoid, if the current is in the anti-clockwise direction, if I'm looking at it from this side, then the current in the outer solenoid will be clockwise, right? So if I look at it with respect to this observer, then you'll find two solenoids. This is the inner one and this is the outer one. And the direction of the current in the inner solenoid is anti-clockwise, and the direction of current in the outer solenoid is clockwise. Right, so we have given N1, N2 are the number of turns per unit length. Find the magnitude and the direction of net magnetic field at a point first inside on the axis. So we have to find magnetic field at this particular point inside the solenoid on the axis, and then outside the combined system. So for the second part, we know that if we are considering ideal scenario or ideal solenoid, then the magnetic field outside will be 0. So at this point B, the magnetic field will be 0. So for the second part, it will be 0. Now now let us find what is the field at a point on the axis at this particular point. Now we have two sources. Now there are two solenoids. So we have to add field by both the solenoids. Now due to this first solenoid, magnetic field at the axis will be mu naught I times N1. And due to the, and it will be out of the plane. So this is the field out of the plane. So this will be B1, let us say. And due to the outer solenoid, the field will be into the plane. If you curl your fingers in the direction of the current, the thumb is pointing into the plane. So let us say this is B2. So B2 is mu naught I n2, and it is into the plane and this is out of the plane. So the net field will be b1 minus b2, so which will be mu naught I n1 minus n2, right? So from this, and this will be the answer of first part. So I hope the concept is clear to you. Right. So now let us see the new concept where we'll study the force experienced by a current carrying. So force experienced by a moving charge placed in magnetic field and electric field. Right. So if there is a charged particle, say Q, and its velocity is in this direction, V, and let us say this is the plane in which the velocity is contained, and the magnetic field is in this direction. So the magnetic force experienced by this charged particle will be given by this formula, which is Q V cross B, right? It is experimental formula. So with experiments, the scientists are able to figure out this particular formula. So the direction of the force will be along V cross B. If this is the angle theta, so if you have to curl your fingers from V to B, the thumb will give you the direction of the force in case of a positively charged particle. So this is the direction of force. And in scalar notation, or if you want to find the magnitude of this force, it will be Q VB sine theta. And theta is the angle between V vector and the B vector. And if we have a negatively charged particle, then the direction of the force will be opposite to this. It will be from B cross B, right? From B cross B, you can find the direction of the force for negatively charged particle. Let me quickly show you. So if we have a electron and it is going in this direction with the velocity v, and this is magnetic field B, and this angle is theta, then the force on this electron will be in the downward normal to this plane. So this will be the force. Okay, now let us see some important points that we can get from this formula. First thing, the direction of this force is perpendicular to the plane containing V and B that we have discussed. This force vector is perpendicular to B, and this force vector is also perpendicular to V. So we can say F is perpendicular to B, F is perpendicular to V. If force is zero, if velocity is zero, yes, if the particle is not moving, there will be no magnetic force. And force will be zero if the angle between magnetic field and the velocity vector is 0 or 180 degree. Or you can say when velocity is parallel or anti-parallel with respect to magnetic field, the force will be 0. Now, and the force will be maximum when the angle is 90 degree, right? So in that case, we'll get the maximum force, and the maximum value of the magnetic force will be QVB. So do remember this. And if both electric field and magnetic field are present, we can say the net force will be given by this formula. So this is the electric force QE that we've already studied in electrostatics. And this is the magnetic force QV cross B, right? So QE plus QV cross B. So if we do the vector addition of these two forces, we'll get the net force on the charged particle. So now let us see what is the motion of charged particle in external magnetic field. So here we know what is the force, right? Now this angle, it can be 90 degree or it can be an acute angle, right? So we are going to consider two cases when theta is 90, and the second case we'll consider when theta is acute. So let us see the first case. When theta is 90 degree, for example, the magnetic field is into the plane and there is a charged particle. Say it is a positively charged particle, Q, and its velocity is in the right direction. And magnetic field is into the plane. So if I curl my fingers from V to B, the thumb is pointing in the upward direction, right? So the direction of the force experienced by this charged particle will be in upward direction. So this will be the force, and this force is always perpendicular to velocity. And this force will be having a constant magnitude. So F is QVB, which is having a constant magnitude if magnetic field, velocity and Q are constant. So all three are constant, so force is having a constant magnitude. So now we have a force which is perpendicular to velocity and having a constant magnitude. So we have studied the same concept in circular motion. If there is a charge, there is a particle which is moving in a circular path, there will be a centripetal force which is having a constant magnitude, right? Similarly here, the particle will be having a uniform circular motion because this F has a constant magnitude. So it will move in a circular path. And now we have to find what is the radius of this circular path. Let us say the radius is R. This magnetic force will act like a centripetal force because it is moving in a circular path. So we can write this as Fc, which is mv square by r, where m is the mass of the charged particle, v is the speed, r is the radius of the circle. Now from this we can find r as mv by qb. So this relation you should remember, this formula you should remember, and where mv is nothing but the linear momentum, and linear momentum in kinetic energy can be written as root of 2mk, where k is the kinetic energy of the charged particle. If you are accelerating charged particle with the help of a potential difference v, then kinetic energy can be written as q times v. So r can also be written as square root of 2mqv divided by qb, right? So you should remember this. Now since it's a uniform circular motion, if we want to find the time period, to find time period, what we can do, time period will be circumference divided by the speed v, and r by v, so from here r by v is m by qb, right? So it will be 2 pi m by qb. Now that is the time period. If you want to find the frequency of revolution, that will be reciprocal of this. So frequency will be qb by 2 pi m. So all these formulas are quite important, and these derivations are also very important. It can be asked in your board exams. Okay, right. Now let us see the second case when velocity is not perpendicular to magnetic field. So let me show you. So there is a charged particle, say q, positively charged particle, and this is velocity vector, and the magnetic field is in this direction, and this angle is theta. Now first thing what we can do, we want to find the direction, we want to find the motion, right? And what is the trajectory of the charged particle in this field. So first we'll resolve velocity along the magnetic field. So this will be, let me call it as v parallel. So v parallel is v cos theta. V parallel means the component of velocity which is parallel to magnetic field, and there is another component v perpendicular, a component of velocity which is perpendicular to magnetic field. Now, due to v perpendicular, the charged particle will move in a circular path that we have already discussed in case 1. And with the help of parallel, v parallel is in the direction of magnetic field, so there will be no magnetic force if we only consider v parallel. So this v parallel will drift the charged particle along magnetic field. So we can say it helps in drifting q along b uniformly with a constant speed v cos theta. And v sin theta, this component is responsible for rotating this charged particle in a circular path. Provide circular motion. Now if we club both these motions, so we have a circular motion and there is a drift. So if I club this, you will get a helical path. So in this case, the charged particle will move in a helical path. So let me show you. So v cross b, so it is going like this. Let me show you. Right? So that is the helical path taken by the charged particle, and every time when it completes one revolution, it crosses this particular axis. And the distance between these two points is known as the pitch. So the drift along magnetic field in one rotation is known as pitch. Okay, right. So what is the radius of this helical path? So if you want to find the radius, now let us say this is the radius r. And we know the formula of radius in the last section, it is mv upon qb, where v is a velocity which is perpendicular to magnetic field. So we can say r is mv perpendicular upon qb. So it will be mv sine theta by qb. So that is the radius of this helical path. Now what is the pitch? So before that, let us find the time period of one rotation. So t will be 2 pi m by qb. So it will remain same. And what is the pitch? So pitch will be pitch is the displacement in the direction of magnetic field, and it is a uniform motion in the direction of magnetic field. So we can say it will be speed into time. Speed is v parallel and time is capital T. So pitch will be v cos theta times 2 pi m by qb. So we should remember these formulas. Okay, so I hope this concept is clear to you. Now let us see the case when we have both electric field and magnetic field. So I'm taking the very basic case when electric field and magnetic field both are in the same direction. And there is a positively charged particle and its velocity is also in the same direction. So V, E, B all are parallel to each other. So since V is parallel to magnetic field, there will be no magnetic force. So we can say FB is 0, but FE is non-zero. FE, if there is electric field, FE can't be 0. It always be non-zero. Due to this electric field, what would happen? There will be an acceleration produced in the charged particle and its velocity will increase because it will experience. So this positively charged particle will experience electric force in the right direction. So this will be QE. Due to this electric force, there will be an acceleration of QE by m. So the speed will increase with a constant acceleration. So we can say it will be a uniform accelerated motion in 1D, right? Now this is the first case. Now let us see the second case. Let us say the velocity makes some acute angle with electric field and magnetic field. This angle is theta. Now here we can take two components. So this will be v cos theta and this component will be v sin theta. Now in this case, v sin theta component is perpendicular to magnetic field. So it will try to rotate this particle or move this particle in a circular path. And because of because of electric field, there will be a constant acceleration produced in the right direction. And that acceleration will change v cos theta. Now in this case, the pitch is not constant. So the particle will move like this. So first the pitch will less and then the distance will keeps on increasing. So you can say it will be a helical path with increasing pitch. So helical path with increasing pitch. So pitch is increasing at a constant rate. Now let us see the third case in which we have cross field, right? So we're considering a case when the charged particle passes undeflected from the cross fields. So let me show you the case. Let us say there is a positively charged particle and its velocity is in the right direction. It's a positively charged particle, and let us say the magnetic field is in this direction. So this is magnetic field. So this is let us say this is x-axis, this is y-axis, and this is z-axis. So magnetic field is in the negative x-axis, and let us say the electric field is in the negative z-axis. Now due to the electric field, if I show the forces, due to the electric field, there will be a electric force in the downward direction or in the direction of the electric field. And due to the magnetic field, the magnetic force will be in the positive z direction. If you apply V cross B, thumb is pointing in the z direction. So this is FB. Now if I keep velocity such that FB and FE are equal, so we can say FB is equals to FB, Only in that case the particle's velocity will not change. It will be in a uniform motion. That is Newton's first law, right? So there should be no force acting on the charged particle if it is in the state of uniform motion. So Fe should be equals to Fb. So it will be QVB should be equals to QE. So Q will get cancelled out. So V should be E by B. So if the speed of the charged particle is the ratio of electric field and magnetic field, then that charged particle will pass this cross field undeflected. So you have to keep this point in your mind. Now let us see some of the questions that can be asked from this section. A narrow beam of protons and neutron. So proton is basically, we can write it like this with mass number 1. And for neutron, we can write this with mass number 2. Each having the same momentum. Enters a region of uniform magnetic field directed perpendicular to their direction of momentum. Right? So what would be the ratio of the circular path? So we know that radius is given as P upon QB. So they have same momentum, right? So momentum is same, magnetic field is same. So radius is inversely proportional to the charge. So proton has 1 unit of charge and neutron mass is different, right? Narrow beam and each, okay, right. So we have to find what would be the ratio of the circular path. So they will be having same radius, won't be any difference, right? Because they have the same charge. Right, so now let us see the another illustration. So two particles A and B of mass m and 2m having charge q and 2q respectively, both these particles moves with velocity v1 and v2 respectively in the same direction, enters the same magnetic field B acting normally to their direction of motion. If the two forces Fa and Fb acting on them are in 1:2, find the ratio of their velocity. Right. So, so we have given two charges. So we have a particle A which is having mass m and charge q, and there is a particle B having mass 2m and charge 2q. Let us say they have velocity v1 and v2. It is given in the question, and they are entering in a magnetic field which is perpendicular to their velocity. Now force on A will be q v cross b, right? And since velocity and magnetic field are perpendicular to each other, so we can write this as q v 1 b, right? So this is fa and fb can be written as 2q v2 b. Now from this we can find the ratio of velocity, right? So what is velocity? So we have fa by fb will be q v1b upon 2q v2b. So b will cancel out, q will cancel out, and fa by fb is 1 by 2. So we can say v1 by v2 times 2, v1 by 2 v2 is equals to 1 by 2. So we can say the speeds of both the charged particle will be same, right? So I hope it is clear to you. So these are the two forces acting, right? Okay, right. So now let us in another illustration. An electron moving horizontally with a velocity of 4 into 10 raised per 4 meters per second enters a region of uniform magnetic field of 10 raised per minus 5 Tesla, acting vertically upward as shown in the figure. Draw its trajectory and find out the time it takes to come out of the region of magnetic field. Let us see. So let me just magnify this. So this electron is entering cross magnetic field, which is perpendicular to velocity. So velocity is in the right direction. Magnetic field is into the plane. So if I apply V cross B, the thumb is pointing in the upward direction, but it is a negatively charged particle. So the magnetic force should be in the downward direction. So if this is the magnetic force, so the center will be somewhere here. So it will move in a circular path and it will come out like this. right? It will complete a semicircle and will come out. And once it comes out of the magnetic field, there will be no magnetic force. So we can say the electron will complete half circle. So this is the trajectory, and find out the time. So it will be half of the time period. So we know T is 2 pi m by qb. So the time taken will be pi m by qb, right? Or you can also look at it from the angle. So this angle will be 180 degree. So if it is 180 degree, it will be for one complete rotation, it will be 360. So for 180, it will be half of the time period. So pi m upon qb. So and we can substitute the value. So mass is 9.1 into 10 raised to power minus 31, and charge is 1.6 into 10 raised to power minus 19, and magnetic field is 10 raised to power minus 5. So to find the time, speed is not required. So by solving this, we can get the answer. Now let us see another question. A proton and a deuteron having equal momenta enters a region of uniform magnetic field at right angle to the direction of the field. Depict the trajectory in the field. Okay, let us see. Let us say there is a field which is into the plane, and proton and deuteron, let us say they're entering from the same point. So this one is proton and the blue one is deuteron, and both have the same momenta. So and we know that mass of the deuteron is 2 times the mass of proton. So let me take mass of proton as m. So mass of deuteron will be 2m. So momentum of deuteron will be 2m times velocity of deuteron, and momentum of proton will be mass times velocity of proton. Since they have same, okay, right. So we let us find the radius. So radius is momentum divided by qb. So magnetic field is same, momentum is same, even they have same charge, right? If they have same charge, we can say, and both are positively charged particles, so they will be having same radius. And if I show the force, both will experience force in the upward direction. So both will follow the same trajectory, right? Like this. So there will be a force in this direction, and this proton will come out after completing half circular path. Similarly, the deuteron will also follow the same circular path of same radius, and it will also come out with the same speed. If this is Vd, then it will come out with the same speed, because magnetic force is always perpendicular to velocity and it does not do any work. Okay, now let us see another question. A point charge q moving with speed v enters a uniform magnetic field v that is acting into the plane of the paper shown in the figure. What is the path followed by the charge q, and in which plane does it move? Okay, right. So since the velocity and magnetic field are perpendicular, and if I apply v cross b, the thumb is pointing in the downward direction. So this is the direction of force. So it will follow a circular path in xy plane. This is the center which lie in the xy planes. It follow a circular path in xy plane. So this will be xy plane. How does the path followed by the charge gets affected if its velocity has a component parallel to the magnetic field? It will be a helical path. We have already discussed this. If an electric field E is also applied such that the particle continues moving along the original straight line path, what should be the value, what should be the magnitude and the direction of the electric field? Okay, right. So if you look at this case, if I apply V cross B, the thumb is pointing in the downward direction. So this is the direction of magnetic force. To balance this magnetic force, the electric field has to be in the upward direction. So that is the direction of electric force. And QE should be equals to QVB, and V should be equals to E by B. So E will be equals to V times B. That is the magnitude of electric field, and it should be pointing in the positive y direction. So we can say electric field will be VB J cap. Got it? Right. Now let us say one more question. A long straight wire AP carries a current I. A proton P travels with a speed V parallel to the wire at a distance d from it in a direction opposite to the current. As shown in the figure, what is the force experienced by the proton and what is the direction? Now we know that due to the current carrying wire, the magnetic field will be the concentric circles like this, right? So if I draw a circle like this, so at this particular point, the magnetic field will be into the plane. So that is the direction of magnetic field into the plane at the location of the proton. And if I apply right hand curl rule, so from V to V cross B, if I apply V cross B, the thumb is pointing in the right direction. So this is the magnetic force. So what is the force experienced by the proton? So the magnetic field by a current carrying conductor is mu naught I upon 2 pi d, right? That we have already derived previously. And this force will be QVB. It's a proton, so Q will be E, and V and B are perpendicular, so it will be QV cross B, right? It will be VB sine 90 degree. So it will be EVB. And B is mu naught I upon 2 pi d. So that is the answer of this question. So, and this force will be in the right direction. Okay, now let us see the next concept, the force experienced by a current carrying conductor placed in magnetic field. Right, so let us say we have a conductor which is having a current I. So there is a conductor and there is a current I, and we are considering that much length. So let us say this length is dl, and so the electrons must be drifting in the left direction opposite to the direction of the current that we already studied in current electricity. Now I want to find number of charge carriers in this region, and how we can find that. So I can say number of charge carriers will be n is the number density or number of charge carriers per unit volume times the volume of this region. So this will be area of cross section times dl. So that much charge, if I multiply this with the charge of one carrier, so it will be E, right? So that much charge is crossing the right cross section, let us say in time t. Let us say the electron takes time t to cover distance dl. So we can say charge entering right cross section in time t will be NADL times A. So that much charge is crossing in time t. So I can so if there is a charge which is NADL times E, which is placed in a magnetic field, let us say this is the velocity, right, VD, and let us say this is the magnetic field. So what is the force experienced by this charge? So that will be NADL times E. Since it's a negatively charged particle, I'll put up a negative sign. So Q VD cross B. Now in this case, VD is in the left direction and DL is in the right direction. So we, for every current element, we'll always take the direction of the current element along the current. So I can say minus VD is along DL, right? So I can write this like this. So NAVD times E will be DL cross B. Can you see? So I can write it like this. And we have seen this relation I upon A N E is equals to VD. So from here I can say this factor is nothing but I times dl cross B. So if there is a current element which is placed in external magnetic field, the force experienced by that current element will be I dl cross B. If B is constant, if B is constant, then the, let us say this is df, right? If B is constant, then F can be given as integral dB. So it will be I integral dl cross B, right? So we don't have to do integration of B. So we can take B outside and we have to integrate only dl vector. So dl vector is what? So if this is the wire and this is our dl vector, so integral dl will be the vector addition of all these current elements. So if I do the vector addition of all these elements, so we have connected these vectors in a particular order. So the resultant will be a vector starting from the tail of the first vector till the head of the last vector. So let me call this vector as L. So this can be written as I L cross B. So even if I have a irregular shaped wire, the 2 points which is of more concern would be the endpoints. You have to join the endpoints and you will get the L vector. So by using this formula, if we have a uniform magnetic field, we can find the force on a current carrying conductor. Now let us see the application of this. A straight wire of mass 200 grams and length 1.5 meter carries a current of 2 ampere. So there is a wire which is carrying 2 ampere current. It is suspended in the mid-air by a uniform magnetic field B. What is the magnitude of the magnetic field? Let us say this is the wire and it is having a current 2 ampere and its mass is also given, so it means there will be a gravitational force and this gravitational force will be 0.2 kilogram times the acceleration due to gravity. And to balance this gravitational force, the magnetic force has to be in the upward direction. So this is the magnetic force. To have this magnetic force, if current is in the right direction, and the L vector, the formula that we have seen, I L cross B, this L is in the direction of the current. So L is in the right direction. So magnetic field has to be into the plane to have a force in the upward direction. So here the magnetic field is into the plane. So this FB will be I, L is 1.5 and B is not given. So we have to find the value of B. So these two forces should balance each other for to suspend this wire in midair. So Fg equals to Fb. So we have 0.2 times 9.8 is equals to 3 times B. So B will be 1.96 by 3. So that will be 0.653 Tesla. So it will be 0.65 Tesla. So that should be the answer of this question. Right, now let us see another question. A square loop of side 20 centimeter carrying current 1 ampere is kept near an infinite long straight wire carrying a current 2 ampere in the same plane as shown in the figure. Calculate the magnitude and the direction of the net force experienced on the loop due to the current carrying conductor. Okay, I'll come back to these questions. Let me first explain you one more concept, and that is the force on parallel currents. Let us see. So we have given two infinite current carrying wires. Let us say it has a current I1 and there is another wire which is parallel to this, and it is also carrying this also carrying current in the upward direction, and the current is I2. Now we want to find what is the force of interaction between these two wires. So what I'm going to do, I will consider a particular length. Let us say I have considered that much length of wire 2. Now first I'll find the magnetic field produced by the first wire at the location of L. So that magnetic field will be by applying a right hand curl rule. So the field at the location of the second wire will be into the plane. So the field, this is B1, let us say, right? And B1 is mu naught I1, and let us say this distance is D upon 2 pi D. So this formula we have already derived by using Ampere's circular law. So the force experienced by this element will be, so force on this length will be I2 times, I2 is the current, L cross B1. Now L vector and B are perpendicular to each other, so I can write this as I2. L and B is mu naught I1 upon 2 pi D. Since they are perpendicular, so sine 90 will be 1. So the force F2 by L will be mu naught I1 I2 by 2 pi D. Right? So this is the force experienced by the second wire per unit length. So force per unit length experienced by 2 due to field by 1. So 1 is producing the field at the location of the 2, and the 2 is experiencing a force. Now let us find the direction of the force. So force is in the direction of L cross B. So L is in the upward direction, B is into the plane, so the force is in the left direction. Similarly, if we find the magnetic field of the second wire at the location of the first wire, then we will get the force on the first wire in the right direction. Now by Newton's second law, or sorry, by the Newton's third law, these two forces will be equal and opposite. So I can say this is the force on second wire due to the first wire, and this is the force on first wire due to the second wire. So F12 will be negative of F21, equal and opposite. So we can say force on 2 by 1 divided by L should be equals to force on 1 by 2 divided by L, and both will be equals to mu naught I1 I2 upon 2 pi D. Right? So now we know this concept. Let us apply this concept to solve this question. So we have given a infinite current carrying wire, and we have a square loop. So let us say this point is A, this point is B, this point is C, and this point is D. Now this AB has a length 20 centimeter, and we have seen if there is a two parallel currents in the same direction, they will attract each other. So it will experience force in this direction, right? So let me call this force as F1. And when we have anti-parallel current, so at this location, the magnetic field will be into the plane. So L cross B is in the downward direction. So on this section, the force will be in the downward direction. So this will be F2. So what is F1? So F1 per unit length, which is 0.2, will be mu naught I1 I2. I1 is 2, I2 is 1 upon 2 pi D, and D is the distance between the two wires, so it will be between AB and the infinite wire is 10 centimeters, so 0.1. So we can say F1 will be, so this decimal will get cancelled out, so we have this 2 will get cancelled out, so we have 2 mu naught upon pi Newton, right? Similarly, we can find F2, so that will be mu naught times 2 times 1 divided by 2 pi D. Now the distance between the infinite wire and section DC will be 20 plus 10, so 0.3 per unit length, which is 0.2. So this decimal we can cancel, 2 will get cancelled. So F2 will be 2 mu naught upon 3 pi. Now let us look at the section DA and BC. So if I take a small element, let me take say a small element at a distance r, right? So at a distance r, I am taking a small element. Now on this small element, what is the direction of magnetic force? So L vector is in the upward direction, magnetic field is into the plane, so it will be in the left direction. So at the same perpendicular distance, if I consider an element in the section BC, so L is in the downward direction and the magnetic field is into the plane. So the force is in the right direction. So this is DF and this is DF. Now these forces will get cancelled out. So for two symmetrical elements on section AB, AD and BC, the forces will get cancelled out. So we're left with only F1 and F2. So the net force on the loop will be F1 minus F2. It is F1 minus F2 because AB is closer to the wire, so the field is much stronger at AB. So the force of so F1 will be having a greater magnitude. So we can simplify this, and F it will be 2 mu naught by pi minus 2 mu naught by 3 pi. So this will be 4 mu naught by 3 pi, and we know that mu naught is 4 pi times 10 raised to power minus 7 divided by 3 pi. So this comes out to be 16 by 3 into 10 raised to power minus 7. So that is the net force on the loop, and it will be attractive force. Right? So it will be in the upward direction. Okay, right. So now we know this these concepts. Okay, this is already discussed. Okay. A wire AB is carrying a steady current of 12 ampere and is lying on the table. Another wire CD carrying 5 ampere is held directly above AB at a height 1 millimeter. Find the mass per unit length of the wire CD so that it remains suspended in its position when left free. Okay, when left free means there will be a magnetic force experienced by the wire which was placed on the table, and that magnetic force should balance the gravitational force. The similar question we have already done. So let us see. So we have given a wire, and let us say it has a mass per unit length lambda. So its mass will be lambda times L. So it is experiencing a weight lambda times L times G, and there will be a magnetic force due to the other wire CD, which is having a current 5 ampere. Let us say here the current is in the right direction, it is also having the current in the right direction, and this current is 12 ampere and this is 5 ampere. Let us say this force is F. Now this F per unit length will be mu naught 5 times 12 divided by 2 pi d, where d is the distance between them, at a height of 1 millimeter. So this distance is given as 1 millimeter. So this will be 10 raised to power minus 3. So F will be 60 mu naught upon 2 pi times 10 raised to power minus 3 times L, and the length is L, right? So that is the force. Now this force should balance the gravitational force. So these two forces should cancel out each other. So we can say it should be equals to lambda L times G. So lambda will get cancelled out, and we have to find lambda. So it will be 60 into 4 pi times 10 raised to power minus 7 divided by 2 pi into 10 raised to power minus 3 times G. So this will give us 2. So we have 120 by G into 10 raised to power minus 4. Now if I take G as 10, it is already given in the question, you have to take it as 10. So this will get cancelled out. So it will be 1.2 into 10 raised to power minus 3 kilogram per meter. So that is the answer of this question. Okay, right. Now let's see another question. So two long and parallel straight wire carrying current 2 ampere and 5 ampere in opposite direction are separated by a distance 1 centimeter. Find the nature and the magnitude of the magnetic force between them. So if we have anti-parallel current, they will repel each other, as we have already seen. To the parallel current, they attract. So here the nature will be repulsive. And what is the magnitude? So it will be given by this. So F by L will be mu naught I1 I2 by 2 pi d. So F will be mu naught 2 times 5 by 2 pi, and d is 1 centimeter 10 raised to minus 2 multiplied with the length length, per unit length we have to calculate now. Force between them. Yeah, so force per unit length will be this, right? Because length is not given in the question. So we have to find, we can only find force per unit length. So this will be 4 pi into 10 raised per minus 7 times 5 upon pi into 10 raised per minus 2. So this will be 2 into 10 raised per minus 4 Newton per meter. So that is the force per unit length. Right, so now let us see what is the definition of ampere. Okay, so let us say we have two parallel wires, right? And we know that when we have two wires with current in the same direction, they attract each other. Let us say we have placed these two wires at a distance 1 meter apart, and the force of attraction per unit length is 2 into 10 raised per minus 7 Newton per meter, right? If that is the force of attraction between them, then we can say in both the wire the current will be 1 ampere each. So let us see how we'll get this force. So if it is 2 into 10 raised per minus 7 and it is F by L, and the formula is mu naught I1 I2. So here I have taken same current divided by 2 pi d. Now d is 1, so this will be mu naught I square upon 2 pi times 1. So we can say 2 into 10 raised per minus 7 is equals to 4 pi into 10 raised per minus 7 divided by 2 pi times I square. So from here, this 2 pi will give us 2 in the numerator. So this will give us I equals to 1 ampere, right? So that is the definition of 1 ampere. So what we can say, if we have two parallel wires carrying this current, same current in the same direction, equal current in the same direction, and they're kept at 1 meter apart, and they are attracting each other with a force of 2 into 10 raised per minus 7 Newton per meter, then we can say the current in both the wires will be 1 ampere each. Now let us see the current loop as a magnetic dipole. So if you look at the magnetic field lines by a current carrying coil and by a bar magnet, the pattern is quite similar. So we can say a current carrying loop behaves like a magnetic dipole. Now what is magnetic dipole? Let us understand that. If I have a current carrying coil which is having n turns and this radius is r, then we have derived the field at a point on the axis, and the field will be mu naught I r square n upon 2 times x square plus r square raised to power 3 by 2. Now if r is very small in comparison to x, then we can say r square will be even smaller than x square. Then x square plus r square can be written as x square, where x is the distance of this point P from the center of the coil, right? I is the current. So the, sorry, not electric field but magnetic field. So magnetic field will become mu naught I r square n divided by 2 x square raised to power 3 by 2, and this can be written as mu naught I r square n divided by 2 times x raised to power 3. If I further rearrange the terms, if I divide and multiply with 2 pi, then I will get 2 times mu naught I pi r square times n divided by 4 pi x cube. Now if you look at this formula, if I show you the electric field by a electric dipole at a point on the axis, if there is an electric dipole P and there is a point and we want to find the field at this particular point. So in case of a short dipole, the electric field was 2 kp by r cube, right? Similarly, in this formula, this term is known as magnetic dipole of the coil, magnetic dipole moment of the coil. And we are also getting this 2 factor, right? So this is the 2 factor, and this is x cube. Here we have r cube, and instead of k, there is a mu naught upon 4 pi, right? So this term is known as magnetic dipole moment. So do remember this. For a current carrying loop, magnetic dipole moment, so I'm showing it with capital M, will be N I A, where A is the area bounded by one of the loop. So in this case, it is pi r square, and its direction will be along the direction of the area vector. And how we can find the direction? If you curl your fingers in the direction of the current, the thumb will give you the normal, right? So if this is the coil and the current is in this direction, if I curl my fingers, the thumb is pointing in the upward direction, so I can say the magnetic dipole moment will be in this direction. And if this area is pi r square and the current is I, then magnetic dipole moment will be I pi r square. If there are n turns, then we can multiply this with n turns. So I hope magnetic dipole moment is clear. Now let us see a question. Reduce the expression for magnetic dipole moment of an electron orbiting around the central nucleus. So there is an electron and it is orbiting around a nucleus of charge Ze plus, an electron is having a charge negative E. And let us say the speed of the electron is V, and we want to find the magnetic dipole moment of this electron. So we know that if there is a current, there is a charge which is moving, it will constitute a current. So here the current will be given by the charge divided by the time period, where time period is the time taken by the electron to cover one circular path. So one circular rotation around the nucleus. So this will be E divided by 2 pi r. R is the radius times the speed. Okay. Now this is the current. So the magnetic dipole moment will be I times pi r square. So this comes out to be E V upon 2 pi r times pi r square. So pi will get cancelled out, r will get cancelled out. So this will be EVR upon 2. Right. So now if I multiply and divide by mass of the electron, now this term MVR is known as the angular momentum of the electron about the center. Right. So M will be equals to E by 2M times L. Since the electron is revolving in the anti-clockwise direction, but the current will be in the opposite direction, so we can say the angular momentum of this electron will be out of the plane. So we can say L vector will be out of the plane, but the corresponding magnetic dipole moment will be into the plane because the current direction is clockwise. So it is into the plane. So M is into the plane. So I can say magnetic dipole moment will be negative of E by 2M times angular momentum. So that is the formula that we have to remember. Okay, right. So that we have seen magnetic dipole moment of a current carrying loop. So formula will be NIA, right? Its magnitude. So now we have understood what is magnetic dipole moment. Now let us see what is the torque experienced by a current carrying loop placed in uniform magnetic field. So this is so we have given a diagram where there is a loop, a rectangular loop, and its plane is making an angle of theta with xz plane, right? So this angle is theta with the xz plane, and this loop has a current I. So if you look this plane from the x-axis, this is the view, right, by this observer. So in this branch, in this segment, the current is in this direction. So this is the direction of the current in the loop, right? So so in the side view, the current is coming out and this current is going into the plane. So if I show the forces, in this case, the magnetic field B is B J cap. It is in the right direction. And let me also name them. So let us say this is P, this is Q, this is R, and this is S. Now PQ is along I cap and RS is along negative I cap. So magnetic field is in the J cap direction. So if I apply force, so what is the force experienced by PQ? It will be IL cross B. So the thumb is pointing in the upward direction. So this is the direction of the current. This is the field. So it will be IL cross B. It is in the upward direction. So I can say F2 will be I, L will be B, right? Times magnetic field. And this force is in Z direction. So you can say K cap. Similarly, F4, which is the force experienced by RS segment, and this will be L cross B, so it is in the downward direction. So it is in the downward direction. So I can say IB small b times minus K cap. Now if we try to find the force on QR and PS, so the force on QR, so if we do that, so it comes out to be in the positive X direction. So we can say F1 will be I A is the length of QR times magnetic field times I cap, and force on the segment SP will be IAB times minus I cap. So what is the net force? So net force will be 0, right? So when we have a closed loop placed in uniform magnetic field, the force on that will be 0, because we know that dF is I dl cross B, and this can be written as IL cross B. Net force will be written like this. So in case of a closed loop, this L vector will be 0 for closed loop, right? So the force will be 0 in case of a closed loop, current carrying loop. Right, but the line of application of F2 and F4 is not same, so there will be a couple, or there will be a torque. Now let us find the torque. So let us take this O as the axis of rotation, and O is at a distance of x from QP. So this is x, and it is at a distance of A minus x from RS, right? So let us find the torque. So F2, the line of application of F2 is at a distance of, we can say this length is x, right? So it will be x sine theta. So we can say F2 times x sine theta, and both the forces will produce clockwise couple, right? So we can say F4 plus F4 times A minus x sine theta, right? Now this perpendicular distance is A minus x sine theta, because this angle is theta, right? So that should be equals to, this is the torque, and the magnitude F2 is IB times capital B x sine theta, and the magnitude of F4 is IB capital B times A minus x sine theta. Now this x sine theta term will get cancelled out. So we are left with IB capital B A sine theta. So that is the torque, and B times A is nothing but the area of the coil. So we can write this as I A B sine theta. And we have already discussed that I times A is nothing but the magnetic dipole moment if we have a single coil or single turn. So we can say mb sine theta is the torque, and this can be written as m cross b, right? So this is the torque experienced by a current carrying loop placed in uniform magnetic field. And what is the direction? So m is in the direction of the area vector. And how to find the area vector? We have to curl our fingers in the direction of the current. The thumb will give us the direction of the area. So this is the magnetic dipole moment. So if we take the cross product of magnetic dipole moment with magnetic field, we will get the torque. So do remember this formula. Now let us see some questions based on this concept. A square shaped plane coil of area 100 square centimeter of 200 turns carries a steady current of 5 ampere. So we have given area, that is 100 square centimeter, and number of turns is given as 200, and the current is 5 ampere. If it is placed in uniform magnetic field of 0.2 Tesla acting perpendicular to the plane. So if this is the plane acting perpendicular to the plane of the coil. So there is a field B which is acting perpendicular to the plane of the coil. Calculate the torque on the coil when its plane makes an angle of 60° with the direction of the magnetic field. Okay, right. So it is saying when if this is the coil, and let us say this is the current. So this will be the magnetic dipole moment. When its plane makes an angle of 60°. Okay, and if this is magnetic field and the plane is making an angle of 60°, then the angle between magnetic dipole moment and magnetic field is 30°. So the torque will be mb sine 30°, right? So what is magnetic dipole moment? Magnetic dipole moment is nia times b sine 30°. So n is given as 200, current is 5, area is 100. Let us convert this into SI units. So 10 raised to power minus 4 multiplied with magnetic field, which is 0.2 Tesla, times sine 30, which is 1 by 2. So this will give us 100 here. So we have, and this 5 and 0.2 will be 1. So 1 into 10 raised to power 4 minus 4. So this comes out to be 1 Newton meter. So 1 Newton meter is the answer of this question. In which orientation will the coil be in stable equilibrium? So as we have studied in electrostatics, if electric dipole and electric field, if they are in the same direction, then it is the case of stable equilibrium. Similarly, in case of a magnetic moment, if this is the magnetic dipole moment and this is the magnetic field, then we can say it is the case of stable equilibrium. If they are in anti-parallel direction, in that case it will be unstable equilibrium. So this is the case, right? When M is parallel to B. Okay, a short bar magnet of magnetic moment 0.9 joule per Tesla is placed with its axis at 30° to the uniform magnetic field. So this is magnetic dipole moment and this is the magnetic field, and this angle is 30°. It experiences a torque of 0.063 joules. Not joule, it should be Newton meter, right? Calculate the magnitude of the magnetic field. Okay, so torque is mb sine theta. Torque is given as 0.063. Magnetic dipole moment is 0.9. So we have to find the magnetic field. So this comes out to be 63 into 10 raised to power minus 3 divided by 9 into 10 raised to power minus 1 multiplied with 2. So that is the magnetic field. So this is 9. So 18 into 10 raised to power minus 2 Tesla. So we can say B will be 1.18 Tesla, right? So that is the magnitude. In which orientation will the bar magnet be in stable equilibrium in the magnetic field? When it is pointing in the direction of magnetic field. So when M and B are in the same direction, when the angle between them is 0. Now let us see one more question. A closely wound solenoid of 2000 turns and cross section 1.6 into 10 raised per minus 4 square meter carrying a current of 4 ampere is suspended through its center, allowing it to turn in a horizontal plane. Find the magnetic moment associated with the solenoid. So for the first part, we have to apply NIA, that is the magnetic dipole moment. So N is 2000, I is 4, and area is 1.6 into 10 raised per minus 4. So if you simplify this, so we have 16 times 4, it will be 64, 6.4. 6.4 times 2 will be 12.8 multiplied with 10 raised per minus 1. So this will become 1.28 ampere meter square. So that is the magnetic dipole moment. Now the torque on the solenoid, if the horizontal magnetic field of 7.5 into 10 raised to minus 2 Tesla is set up at an angle of 30 degree with the axis of the solenoid. So this is the magnetic dipole moment, and this angle is 30 degree. This is the magnetic field. Now we have to find the torque, and torque will be mb sine theta, sine 30. So B is 7.5 into 10 raised per minus 2, and the magnetic dipole moment is 1.28 times sine 30 is 1 by 2. So this will be 0.64, and this can be written as 1/5 by 2, 15 by 2 times 0.62 times 10 raised per minus 2. So this will be 0.31. So this will be 310 plus 155. 310, 155, so 564, so 465. So it will be 4.65 into 10 raised per minus 2 Newton meter. So that is the answer of second part. Right. So now let us see what is a moving coil galvanometer. Right. So in moving coil galvanometer, there is a iron core, and on this iron core, the conductor or a wire is being wrapped like this. So let us say there are n turns. So let us say n is the number of turns and I is the current, and let us say A is the area of one of the turn, right? Area of loop. So the purpose of galvanometer is to detect a very small amount of current. So let me show you the cross-sectional view. So this is the magnet, and this is the north pole, this is the south pole, and we have a soft iron core. Now the purpose why we are using soft iron core, because if you place soft iron in external magnetic field, it get magnetized. So instead of a horizontal field lines, we will get a radial field line. Let me show you. Here the field lines will be like this. And what is the purpose of this radial field line? That at any orientation of the coil, the field will be parallel to the plane of the coil. So if I show you the coil, so this is the coil, right? And let us say this is the current, right? Like this, the current is flowing in the coil. Now, if I want to find the direction of magnetic dipole moment, so it will be normal to the plane. So if I curl my fingers in the direction of the current, thumb will give us the direction of the magnetic dipole moment. So this is the direction of magnetic dipole moment, and the magnetic field is parallel to the plane. So now the angle between them is 90 degree. So what is the torque? So torque will be M cross B, which comes out to be NIA B sine 90 degree, which is nothing but NIAB. So that is the torque produced by the current in the coil. Now there are torsional springs connected to the axle, right? So there are torsional spring. Now these torsional spring will exert torque in the opposite direction, and when the torque of spring balances the torque of the field, then we can say the pointer will get stabilized. So this pointer will get stabilized and it will give us some reading. So we can say pointer gets stabilized when torque due to the field get balanced by the torque due to spring. And the torque due to spring is directly proportional to the deflection. So we can say it is equals to C theta, where C is known as the torsional constant of the spring. C is torsional constant. So we can say NIAB should be equals to C times theta, or sometimes we'll write it as K times theta, right? So from here I can find I by theta as C divided by NAB, right? So N the term theta by I, which will be NAB by C, is known as current sensitivity, right? So it tells us what is the deflection per unit current. So greater deflection for a given current, we can say more the sensitivity, right? Now if I want to find the voltage sensitivity, what we can do? So instead of I, we require voltage. So what we can do, we can divide both side, the denominator, we can divide both side by R. So if I divide both side by R, we'll get NAB divided by CR. Is it clear? Now this IR is nothing but the potential difference across the coil. So we can write theta by V equals to NAB upon CR. And this term theta by V equals to NAB by CR is known as voltage sensitivity. So we should remember these two results. Okay, now let us see that the problems that can be formed from these formulas. So define the current sensitivity that we've already seen. This is theta upon I, which is equals to NAB divided by C. Okay, and the coil area of galvanometer is 16 into 10 raised to power minus 4 square meter. It consists of 200 tons of a wire and is in a magnetic field of 0.2 Tesla. The restoring torque constant of the suspension fiber is 10 raised to power minus 6 Newton meter per degree. So basically this is C, right? Assuming the magnetic field to be radial, and calculate the maximum current that can be measured by the galvanometer if the scale can accommodate 30-degree deflection. So we have given deflection. So what is the maximum current that can be measured? So we can apply this formula. So I will be theta C divided by NAB. So theta is given as 30. So we can write theta in terms of radians. So it will be pi by 6. And C is 10 raised to power minus 6. Number of turns we have given as 200. And area is 16 into 10 raised to power minus 4. And magnetic field is 0.2. Right? Now from here we can find current in amperes. So by simplifying this, we'll get the answer. Right, so now let us see the illustration. So to increase the current sensitivity of a moving coil galvanometer by 50%, its resistance is increased so that the new resistance becomes twice its internal resistance. By how much faster does it voltage sensitivity change? Okay, right. So we know that current sensitivity, which is theta by I, this is the, let us say this is the original value. Now it has increased by 50%, so it has become 1.5 times theta I. And voltage sensitivity is theta upon IR, that is the original value, and it has become, so theta by I has become 1.5 theta by I, and R has become double, right? So it becomes double, so 2R. So we can say the new voltage sensitivity is 1.5 by 2 theta by IR. So it has changed by this factor. So earlier it was theta upon IR, now it is 1.5 by 2 theta upon IR. Now what is the percentage decrease? Let us find that. Percentage decrease will be so it will be theta upon IR minus 1.5 upon 2 theta by IR upon original value theta upon IR times 100. So this will be 1 minus, and 1.5 by 2 can be written as 3 by 4 upon 1 into 100. So that will be 1 by 4 times 100. So it will be 25%. So the voltage sensitivity will decrease by 25%. Right. So now let's see how we can convert a galvanometer into ammeter and voltmeter. So let us see how we can convert this into ammeter. Now an ideal ammeter has zero resistance, right? So why it has zero resistance? Because it is connected in series. If it has some substantial resistance, then it will alter the resistance of the circuit. So in order to convert a galvanometer into ammeter, we have to connect a very small resistance in parallel to the galvanometer. Now this is the galvanometer, and we have connected a resistor which is known as shunt in parallel. And suppose we want to measure the current I. And here we'll define another very important current, that is Ig, which is known as full scale deflection current. So if we pass Ig current through the galvanometer, it shows maximum deflection. So to measure I, let us say Ig is flowing through the galvanometer and the remaining current will flow through the shunt. Since shunt and galvanometer are connected in parallel, so the potential drop across them will be same. So I minus Ig times S should be equals to Ig times G, where G is the resistance of the galvanometer. Now from here we can find S value, which is Ig times G upon I minus Ig. In most of the question, Ig is very small in comparison to the current that we need to measure. So sometimes it can be written as Ig G upon I, only I in the denominator, because if Ig is very small in comparison to I, then we can apply this. We can apply this approximation. Right, so now let us see a question. A galvanometer has a resistance of 30 ohms. It gives full scale deflection with a current of 2 milliampere. So Ig is given to us, that is 2 milliampere, and G is given as 30 ohms. Calculate the value of resistance needed to convert it into an ammeter of range 0 to 0.3. So we have to measure maximum current of 0.3 in the circuit. So if this is the circuit diagram, so this is galvanometer and this is the shunt, and 0.3 ampere current is coming. So we can say 2 milliampere will flow through the galvanometer, and the remaining current 0.3 minus 2 milli will flow through the shunt. So 0.3 minus 2 into 10 raised per minus 3 times S should be equals to 2 into 10 raised per minus 3 times G, and G is given as 30. So this will be 60 times 10 raised per minus 3 and this will be 300, or I can write this as 300 times 10 raised per minus 3 minus 2 into 10 raised per minus 3 times S. So the shunt will be 60 into 10 raised per minus 3 upon 298 times 10 raised per minus 3. So if we simplify this, it will be 60 divided by 298. So it comes out to be 0.20 ohms. So the shunt has this resistance 0.20 ohms. So if we have that shunt, we can measure current up to 0.3 ampere in the circuit. Now let us see one more question. A moving coil galvanometer of resistance G gives its full scale deflection when the current Ig flows through this. It can be converted into an ammeter of range 0 to I when a shunt of S is connected across its coil. If this galvanometer is converted into an ammeter of 0 to 2I, range of 0 to 2I, find the expression for the shunt required to in terms of S and G. Okay, right. So first what we have given. So there is a galvanometer and we have connected a shunt which is S, and the full scale deflection current is Ig, and here we have I minus Ig. So we can write I minus Ig times S is equals to Ig times G. Now what we have done, we have changed the shunt so that we can measure more current. So now the circuit will look like this. So let us say this is the new shunt value S prime, and here the current is 2I. So here we have Ig, and here it will be 2I minus Ig. So we can say 2I minus Ig times S prime will be Ig times G. So what we can do? So we have to find answer in terms of S and G. So we have to eliminate Ig, right? Okay, right. So from here I can say Ig will be Is upon S plus G, and from here Ig will be 2I S prime upon S prime plus G. Okay, so let us equate these two equations. So Is upon S plus G should be equals to 2Is prime upon S prime plus G. So I will get cancelled out. So S prime will be S prime plus G times S, and this S prime plus G plus S, and we have 2 here, so it will be 2 times S plus G. Okay, so from here I can say S prime will be 2S plus 2G minus S equals to 2S plus 2G minus S plus equals to GS. So S prime comes out to be GS upon S plus 2G. So that is the answer of this question. Now let us see how we can convert galvanometer into voltmeter. Ideal voltmeter has infinite resistance. So if we want to convert a galvanometer into a voltmeter, so we have to connect a very high resistance in series. So this is the galvanometer, and we have connected a resistance R in series. And when we pass full scale deflection current, the potential drop across the galvanometer and the resistor is V. So we can say V is equals to Ig times G plus R, and from this we can find the value of R. So V upon Ig minus G will be the resistance that we have to connect in series. Right, so now let us see the question. Why is the magnetic field radial in moving coil galvanometer? That we have already discussed. So that the magnetic field and the area of the loop are parallel to each other. A galvanometer of resistance G can be converted into voltmeter of range 0 to V volts by connecting a resistance R in series with it. How much resistance will be required to change its range from 0 to V by 2? So how much resistance will be required? So if I want to have this range, so let me show you. So this is G, and let's say this is R prime. Let me first take it as R, right? And there is a current of Ig, and the voltage drop across this device is V. So we can say V is equals to Ig times G plus R. So that is the first equation. Now we want to decrease the maximum voltage that can be measured with the voltmeter. So this is the galvanometer. Now we have connected a resistor R prime, and the voltage drop across this device is V by 2 when the current is Ig. So we can say Ig times G plus R prime is equals to V by 2. So we have to find the resistance. So what we can do, let us V by 2. So what we can do, so how many unknowns are there? Ig is known to us. Ig is unknown to us. That is not given in the question. G is given in the question. So we can eliminate Ig. So if we divide first and second, so we can say G plus R upon G plus R prime should be equals to V upon V by 2. So this V will get cancelled. So this will be 2. So we can say G plus R is equals to 2G plus 2R prime. So R minus G is equals to 2R prime. So R prime will be R minus G by 2. So that is the resistor that we have to connect in series with the galvanometer to change the range from 0 to V to 0 to V by 2. Now let us see one more question. A galvanometer coil of 50 ohms resistance shows full scale deflection for the current of 5 milliampere. So this is Ig and this is G. How will you convert this galvanometer into an voltmeter of 0 to 15? A very basic question. So this is G and this is R, and the voltage drop across this device is 15 volts and the current is 5 milliampere. So we can say 15 will be 5 milli times G plus R by Ohm's law. So this will be 3. So we have 3000 minus G, which is 50. So R comes out to be 2950 ohms. Right? So here I conclude the video. So I have covered all possible concepts, all derivations and all possible numericals that can be asked in your board exams. So see you in the next video where I'll cover the next chapter, which is magnetic material and magnets. Thank you.